Hi, welcome to part 2 of our lecture on the solar system. In this part of the lecture, we're going to be looking at the inner solar system, which includes the 4 terrestrial planets, Mercury, Venus, Earth, and Mars. Let's start by talking about the Earth and its moon. This is a famous, iconic photograph of the Earth taken from the moon from the Apollo 11 astronauts in 1969. We'll begin by talking about the structure of the Earth's interior. And the basic structure here is the result of the process of differentiation, which we talked about in the last part of this lecture. When the Earth was young and molten, the heavy materials, metals, basically sunk to the center, and the lighter rocks rose to the surface. And of course, then we have an atmosphere around that. So our Earth's structure is based on that idea of how it forms. So around the outside of the Earth is the solid crust of the Earth, which we live on. Underneath that, this blue region in the picture here is the mantle, which is rock, but it's under high pressure and high temperature, so this rock in this region can flow. It's almost sort of like a liquid. And then underneath that is the liquid core of our Earth, which is molten iron and nickel at very high temperatures and high pressures. And then at the very center of the Earth, the iron and nickel are actually solid. So this is the solid inner core. And the reason it's solid in here is because of this extremely high pressure at the center of the Earth raises the melting temperature. So it's not quite hot enough to melt the iron and nickel core here. However, the temperature at the center of the Earth is almost as hot as the surface of the sun. It's something like 9,000 degrees Fahrenheit. The crust of our Earth consists of a thin layer of rock, and the rocky crust is broken up into what are called tectonic plates. And these plates basically are floating on top of the mantle, which is underneath it. And these tectonic plates, most of them are associated with continents. For example, the North American plate, the South American plate, the African plate, etc. And these plates are actually moving slowly relative to each other. And so this plate tectonics creates geologic activity, which we'll talk about next. One geologic feature that sort of highlights the presence of these tectonic plates is the famous San Andreas Fault, which runs along the backbone of California. And the San Andreas Fault, you can see it in this aerial photograph here, is basically where two plates are meeting each other. So on one side is the North American plate, and on the other side is the Pacific plate. And these plates are slowly moving against each other, building up stress. And that stress eventually has to be released, which is in the form of an earthquake. So the San Andreas Fault is capable of producing very powerful earthquakes. This diagram down here shows some more of the so-called plate tectonics, and the idea here is these plates on the Earth are slipping and sliding past each other, and in places where the plates come towards each other, like right here, one plate might be forced down below and the other plate might be pushed up, and you can see where they rub against each other. There's friction and melting underneath the Earth's crust in the mantle, and that can lead to volcanic activity, and also these places where the plates are pushed up creates mountain ranges. So the plate motion results in geologic activity, which includes earthquakes, volcanoes, and mountain formation. Now, the motion of these plates is very slow. It's a few inches per year. In fact, it's been said that the plates move about the same speed as your fingernails grow, which sounds very slow. But over many years, these plates can move a large distance and build up stress to cause earthquakes, or actually push up and form mountain ranges. One of the interesting consequences of Earth's tectonic plate motion is that many years ago, the Earth's geology or map looked very different. In fact, all the continents were once connected together into a sort of a single universal continent called Pangaea about 200 million years ago. And then the continents broke apart and to where they're at today. And one thing you can notice when you look at a map of the world, you can see how the continents look like pieces of a puzzle, and they actually fit together. And so that's one piece of evidence for this tectonic plate motion. The other piece of evidence is that the shorelines of the continents where they broke apart contain the same types of minerals and fossils. One of the features that makes our planet unique from the other planets is the fact that Earth has liquid water. And in fact, the majority of the surface of the Earth is covered with ocean water. So the question comes up, where did Earth's water come from? This is actually not known for sure, and scientists are still debating and researching the source of all this water. But there are several ideas of where Earth's water came from. One of them is that the solar nebula that produced our sun and all the planets when our solar system formed contained hydrogen and oxygen gas. We know that. So the water was formed probably during the initial phase of planet formation. Water is also trapped inside of rocks and lava, which will outgas into the atmosphere during volcanic activity during the early stages of our Earth's formation. Another source of water on our Earth is extraterrestrial. Comets and asteroids are rich in water ice, and during the early phase of our planet's formation, the Earth was being bombarded continuously with comets and asteroids. This is leftover material and debris from the formation of the solar system. So these bombardments from all these comets and asteroids brought water to the planet. And lastly, biological activity took place later on when life took hold on Earth, and photosynthesis from the plants actually produces water as well. So the water on our Earth is probably a combination from these various sources. The next thing we can talk about is Earth's atmosphere. Where did Earth's atmosphere come from? Well, Earth's atmosphere underwent several different stages of evolution. The early Earth had an initial or primeval atmosphere that came from the solar nebula itself, but that was mostly hydrogen and helium, which are the two lightest gases. So these gases would have escaped from Earth's atmosphere very early on. What probably happened next was outgassing from rocks and volcanoes, which would release carbon dioxide, nitrogen, and water vapor. Finally, when life took place on Earth later, certain types of plant life, blue-green algae or cyanobacteria, converted the carbon dioxide in our atmosphere to oxygen via the process of photosynthesis. And so plants made a major change to our atmosphere. It created an oxygen-rich atmosphere that was very different from the initial atmosphere of the Earth. So the oxygen that we're breathing today, and the air that we breathe is roughly 20% oxygen. All that oxygen pretty much came from plants. One thing that's happening now in the modern day is that our atmosphere is changing due to human activity, and this is not a good thing at all. Since the Industrial Revolution started about 150 years ago, we started burning fossil fuels, coal, oil, and gas, which releases carbon dioxide into the atmosphere. So this graph here shows going back about 1,000 years, this is the year down here, starting year 1000 AD, you can see that the carbon dioxide levels in our atmosphere were relatively constant. These were, by the way, this data was taken from samples of bubbles trapped in Arctic ice and other sources like that. But you can see once the Industrial Revolution started, the CO2 levels started climbing dramatically, and they are still going up. And we'll see the consequences of that next. Let's now talk about the greenhouse effect and global warming. So what is the greenhouse effect? Well, the greenhouse effect is a natural process in which sunlight is converted to heat and trapped by greenhouse gases in our atmosphere, such as carbon dioxide, methane, and water vapor. And the greenhouse effect gets its name from the phenomena where a greenhouse, which is basically a glass enclosure where plants can live inside, a greenhouse allows sunlight to enter the greenhouse and warm up the inside of the greenhouse. The heat from the sunlight can't escape because it's trapped inside the greenhouse. And you see the same effect inside your car. When you park your car, even on a cool winter day, if you have your windows rolled up, your car will get warm very fast from that sunlight coming in, and the heat can't escape. So in our planet, something very similar happens. Sunlight can come in through the atmosphere and warm the Earth, but then the Earth tries to cool off by emitting infrared radiation, which is heat. But the infrared radiation is trapped by these greenhouse gases, mainly carbon dioxide and methane. So this greenhouse effect warms up our planet. In fact, the greenhouse effect is a good thing, and it's essential to keep our planet warm. Without our atmosphere and the greenhouse effect, the planet Earth would be a frozen, frigid world, and life almost certainly probably would have never even taken hold on the Earth. However, too much of any good thing is usually not good, and this is the case with global warming. So with global warming, what we're talking about here is the man-made carbon dioxide emissions from burning fossil fuels such as oil, coal, and gas, along with deforesting the rainforests, which, remember, photosynthesis from plants converts carbon dioxide to oxygen, which is a good thing. So we're burning down and tearing down forests, which removes this photosynthesis process. So the combination of emitting more carbon dioxide and removing the rainforests are increasing the CO2 levels and enhancing the greenhouse effect. So remember this graph we just talked about on the last slide. We have seen the carbon dioxide levels in our atmosphere rising dramatically since we started burning fossil fuels at the beginning of the Industrial Revolution. So the problems with global warming are that if the temperature of the Earth increases too much, this will lead to drought, agricultural impact, fires, loss of natural habitats, and extinction of sensitive species. And in addition, melting glaciers and polar ice caps leads to rising sea levels, which causes flooding of coastal cities. So what can be done about global warming? How can we eliminate our dependency on oil, coal, and gas? Well, the answer is almost certainly to use clean, renewable energy. This is energy that comes from resources which are naturally replenished, such as sunlight, wind, geothermal, rain, tides, and waves. Clean renewable energy has no emissions, meaning no carbon dioxide given off, no pollution as a byproduct, and no radioactivity. So using solar panels, windmills, and tapping into the geothermal energy, which is down inside of our Earth, are all ways we can remove our dependency on the fossil fuels. So where did our moon come from? Well, there are several different hypotheses over the origin of our moon that have been proposed over the years. And we don't know actually for sure, but the evidence seems to support the idea that our moon formed as the result of a large impact with the Earth and another large Mars-sized planet early during the formation of our Earth. So this is the proto-Earth here. This is the Earth early on in its formation when it was still in its molten magma state. And this impact from another object in the solar system, in the early solar system, caused basically the ejection of material that later came together and coalesced to form our moon. So this is our current best understanding of how our moon actually formed. So now let's take a look at the other planets of the inner solar system. Let's start with Mercury. Mercury is the planet closest to the sun in our solar system. And it's actually very similar to our moon. In fact, this picture you see here of Mercury looks a lot like our moon. Mercury is small. It's not much larger than our moon. Here it is shown compared to the size of our Earth here. Like our moon, it has no atmosphere. Its surface is hardened lava, and it has a lot of craters like our moon. Being the closest planet to the sun, Mercury has an extremely hot temperature. The side of Mercury that faces the sun is about 800 degrees Fahrenheit. Now, the backside of Mercury, which faces away from the sun, drops down to 280 degrees below zero. So there is over a 1,000 degree swing in temperatures between the day of Mercury and the night of Mercury. And this is because there is no atmosphere to hold heat. Also, remember, because Mercury is the closest planet to the sun, it has the fastest orbit around the sun. And so Mercury takes only 88 days to go around the sun. Here are some really nice pictures of Mercury's surface taken from various missions. These are unmanned missions that were sent to Mercury to orbit the planet and study it. So you can see the craters very similar to our moon. The other thing that I mentioned before was that Mercury has no atmosphere, and there are two reasons for this. Because Mercury is so close to the sun, the atmosphere that it might have had in the past would be extremely hot. And remember, heat and thermal energy means that the gas molecules would be moving very fast. In fact, being that close to the sun, the gas molecules would be able to escape the planet and just fly off into space. And the reason for this is that the planet Mercury has a very small mass. It's the smallest planet, meaning it doesn't have very much gravity to hold that atmosphere. So if the gas velocity of the molecules is greater than the escape velocity, that's the velocity needed to actually escape from the planet Mercury, then the atmosphere will basically just escape off into space. And that's certainly what happened, and the result is no atmosphere left on Mercury. This is sort of a virtual tour of the planet Mercury for what it would look like if you were flying over the planet in a spacecraft. These images here were actually taken by the Messenger spacecraft, which was a robotic satellite orbiter that was sent to Mercury and sent back these amazing pictures of the surface of Mercury. There are a couple interesting things here. They found evidence of water ice that still exists inside some of the craters at the poles of Mercury, where the sun can't get down inside of those craters. And this is my favorite down here. This is the Mickey Mouse crater on Mercury. Let's now turn to Venus, which is sometimes called Earth's sister planet. You can see that Venus and Earth are very similar in size. Earth is just a little bit bigger. Venus has thick clouds and a thick atmosphere, so from space we can't see the surface of Venus. All we see are its cloud layers. But by using radar techniques, we can actually image through the cloud layers and see the surface of Venus. So this is what you're seeing here. This is a radar map of the surface of Venus. So it was originally thought that Venus might be a wet and warm planet because of all these clouds, But now we know that it's not at all. In fact, it's dry and extremely hot. Venus is perhaps the most inhospitable planet in our solar system. The reason for this is that Venus is actually the hottest planet in our solar system. Its surface temperature is about 880 degrees, which is actually hotter than Mercury. Now, why is this? Well, it's because this Venusian atmosphere traps heat. This is the greenhouse effect again. So Venus's atmosphere is mostly carbon dioxide, which remember is a very efficient greenhouse gas. So this thick carbon dioxide atmosphere traps heat and has turned Venus into this scorched planet. These are some pictures taken of the surface of Venus. This picture up here is kind of interesting. This was actually from a Russian spacecraft that successfully landed on the surface of Venus back in the 1970s and lasted for less than an hour before it basically overheated, but it was able to return some images of the surface of Venus. You can see the landing pad of the spacecraft here, but you can see some of the kind of sandy and rocky soil on the surface of Venus. This is a radar image of a mountain on Venus that's 50% taller than Mount Everest. You can also see craters and volcanoes and lava flows in these radar images of the surface of Venus. So Venus suffered from a runaway greenhouse effect that caused the planet to basically fry itself. And remember, the idea here is that carbon dioxide is transparent to visible light. So in other words, sunlight can get in, but heat, infrared, can't get out. So Venus can absorb energy from the sun, but it can't cool itself off. And without oceans to absorb the carbon dioxide from the atmosphere, basically the CO2 effect in the atmosphere caused the greenhouse effect, and it warmed the planet even more. And the thing is here, we have sort of an unchecked feedback mechanism. The higher the temperature got on Venus, the more carbon dioxide was baked out of the rocks through outgassing. So with more CO2 released from the rocks, that created a greater greenhouse effect because carbon dioxide creates the greenhouse effect. So over time, this process just ran away. It got worse and worse and worse. And what's left today is sort of a sobering reminder of what can happen to a planet if the greenhouse effect goes unchecked. Remember, Venus is the hottest planet in our solar system. It's something like 880 degrees on the surface of Venus today. So this is a reminder to us on Earth that we don't want our Earth to heat up through the greenhouse effect and global warming. Let's now leave Venus and go to this nice desert scene here. This image here shows a desert. Now the question is, where is this? Is this Death Valley, California, or is this the Anza Borrego Desert, which is here in San Diego County? Or is this a picture of the deserts from Afghanistan or maybe the Sahara Desert? Or am I trying to trick you here, and is this something completely different? Well, maybe you've guessed it. This is nowhere on Earth. This is actually a desert on Mars, and this is an actual photograph taken from the surface of Mars. It almost gives us a sense like we're standing on the surface of Mars and hiking around and exploring another planet. So Mars is the last planet we're going to explore here in this part of the video because it's the last planet in what we call the inner solar system of the terrestrial planets. And Mars is the most fascinating planet for exploration because we think that Mars was once very Earth-like with water and warm temperatures. Mars is smaller than the Earth. It's about half the Earth's size, but it has many Earth-like features, including a rotation period that's very similar to our Earth's. The Martian day is 24 hours and 40 minutes. The other thing about Mars is its axis is tilted, just like the Earth's is, and this causes seasons on Mars. So Mars warms up during the summer months, and Mars cools down during the winter months. Also, Mars is called the red planet. You can see it's sort of red or ruddy color here. Mars has an atmosphere, but unfortunately it's very thin. It's only about 1% of the pressure of Earth's atmosphere. So most of the atmosphere of Mars escaped because Mars is relatively small. Unfortunately, Mars is, as I mentioned, about half the diameter of the Earth. If Mars was Earth-sized, it might have been able to hold on to that atmosphere, and that would have left Mars perhaps much warmer, and some of the liquid water would probably still be there. Here's another really cool picture taken from a lander, a robotic lander that successfully landed on the surface of Mars, and took a nice picture here so you get a feel for what the Martian landscape looks like. As you can see, it's basically a barren desert, and what you can't tell in the picture is how cold it is here. The average temperature on Mars is about 60 degrees below zero, which is similar to Antarctica on the Earth. In fact, temperatures have been recorded as low as negative 220. However, there have been some warm days during the Martian summer that have reached 70 degrees. But for the most part, the average temperature is extremely cold. So the way to describe Mars is basically a frigid, cold, dry desert. Mars has evidence of past volcanic activity. In fact, one of the volcanoes on Mars, which is called Olympus Mons, it's shown here in this image taken from an orbiter, is more than twice as tall as Mount Everest. So our Earth's tallest mountain, Mount Everest, is about 5 miles tall. Olympus Mons is 13 miles tall. So this is the largest and tallest volcano in the entire solar system. A lot of what we've learned about Mars was taken from several rovers that were sent there and had very successful missions. And there have been multiple successful rover missions to Mars. Two of the most productive missions were called Spirit and Opportunity. They lasted almost 15 years roving around Mars and collecting samples and taking data and measurements. By the way, these rovers were only promised to work for 3 months, and they actually worked for more than a dozen years. These are some of the amazing images that were sent back from these rovers. You can see sand dunes and rock formations. You can see layers of rocks. This is the edge of a crater on the surface of Mars, and here you see some of the hilly Martian landscape. The most fascinating thing about Mars, though, is the evidence that Mars was once a warm and wet planet. So we think that perhaps 4 billion years ago, Mars looked very much like the Earth, with water and continents and lakes and rivers. So the evidence for that past water is still there. For example, there are channels carved out by water. There are dry stream beds, layered bedrock, which formed as sedimentary layers in water, gullies on crater walls, drainage features, dry river deltas, and Martian minerals deposited in water. Just like the Earth, Mars has polar ice caps. And these ice caps grow and shrink depending on the season. This is a picture from space of showing the planet Mars here, and you can see the ice cap up here. And this is an image from an orbiter that flew over the ice cap and imaged it. So these polar caps contain mostly frozen carbon dioxide, which we know as dry ice, but it also contains frozen water ice. An interesting mission to look for water on Mars was the Phoenix Mars lander, and it landed near the Martian polar region, and it scraped down under the soil and it found frozen water ice underneath there, which you can see in these images. Here's our last slide of this part of the lecture. This is just some highlights of another rover that is currently still working on Mars. This is the Mars Curiosity rover, and it's a car-sized rover that landed in 2012, and it's the most advanced robotic science lab ever built. It contains dozens of cameras and scientific instruments. It can scoop up rocks, it can drill holes into rocks, and it can do chemical analysis of the rocks and the soil that it investigates, and it also sends back pictures and images and takes temperature readings and things like that. It's basically looking for, not for life itself, but it's looking for the chemical building blocks of life. There are many highlights of the Curiosity rover mission, but one of the most interesting is it discovered an ancient Martian stream bed which contains smooth, watery, eroded rocks and sedimentary layers very similar to those seen on Earth. So this picture here is of a dry stream bed on Earth, and this is basically the same geologic feature seen on Mars. And by analyzing the shape and how smooth these pebbles are, scientists were actually able to estimate how fast the water was flowing in this ancient Martian stream. So that is our tour of the inner solar system. We will return to Mars a little bit later in the course when we talk about astrobiology, and we'll talk about the possibility that life either existed on Mars or maybe still exists underneath the surface of Mars, where the temperatures might be warm enough for liquid water to still remain. Until then, I will see you in the next part of this video where we will travel to the outer solar system. Goodbye.